My name is Natalie, and I'm going to show you the reason why you break the fan. And I have Benson. My Benson's called Fran Table. And I'm going to show you how you break the fan by Natalie. Oopsie daisy. Just like that, you break the fan. And I made this. So, you cut it with it. See, it didn't break. I press hard, it won't break. Okay. Yep. And you see how there's no fan right here? I had to open this up by Sleeper and Benson and just slide it in. Ta-da! And the reason I got this is from my doll. And I made a smaller version of it.
Hello, my name is Sanji and I'm a 10th grader at the Community School of Naples in Naples, Florida. I invented the silicone eye alpination model, commonly referred to as the seam. Alpination is a fancy word for checking eye pressure. The model is currently patent pending. The eye model consists of a 3D printed eye with a silicone cornea constructed from 3D pieces. The bottom right photo shows a technician using the gold manometer on the seam, which presses on the cornea. This leads to how I developed the seam. My grandfather was diagnosed at age 50 with glaucoma. As a result, he is partially blind in one eye. Concerned, I researched the prevalence of glaucoma. According to the credible organization Prevent Blindness America, 1.9% of the US population in 2010 had glaucoma, which approximates to 3 million people. Their model suggests that in 2050, there will be more than 6 million cases. After researching glaucoma's prevalence nationally, I researched whether ophthalmic technicians had a training tool to practice measuring eye pressure. However, the USPTO and NCBI suggest it does not exist. So ophthalmic technicians practice on staff and patients, which causes painful corneal abrasions from improperly checking eye pressure. This causes staff to not be able to go to work due to pain and causes patients to seek other eye doctors to only encounter the same problem. This leads to the third problem. After interviewing local ophthalmologists, they shared the abundance of plastic syringe caps from eye procedures. This is environmentally detrimental, as plastic is polluting waterways. The accumulated plastic will provide a plastic source for the 3D pieces necessary for the seam. After thorough research, I began the design and prototyping phase. I used a 3D printer for the initial schematics. However, it has occasionally malfunctioned, causing the products to be rugged or too small. Through several iterations, I was able to create a successful eye and mold for the silicone cornea. Creating the silicone cornea also presented difficulties, as the layers were occasionally too thin or too thick. However, through multiple trials, I acquired a cornea that could fit properly into the 3D eye. This was the final product. So why is the seam an effective solution? It raises awareness for glaucoma and promotes the environment. It also reduces the probability of corneal abrasions during training, since it will eliminate practicing on people. Ultimately, I developed a business plan. There are approximately 80,000 eye doctors nationally. 10% market share yields 8,000 seams. Upon interviewing local ophthalmologists, they mentioned they would be willing to purchase the model for $39. I would need funding for a 3D printer and $10,000 for a website and marketing. So year one production of 1,000 models results in a net profit of $15,000. This leads to the marketing strategy. I will attend glaucoma conferences where I will sell to pharmaceuticals manufacturing glaucoma medications, sell directly to eye clinics, and give free seams to Lions Eye Clinics, which are free clinics for impoverished areas. These are my sources. Thank you.
Hello, my name is Lucan Kieser. I'm a junior, and today I'll be presenting about my biofoul removal tool. In order to understand the significance of my tool, one needs to know that since the 1970s, reefs around the world have declined immensely, and in particular, the Caribbean reefs, according to Mark C. Ladd, have died off by almost 80%. Now, this die-off is present around the world, and in particular in the Florida Keys, where I have been diving for community service with the Coral Restoration Foundation, or CRF. CRF's motto is to take fragments of coral, grow them to a sufficient size, and plant them on the reef in order to counteract that death that has been occurring. Now, in order to grow them, they need a stable environment to grow in with lots of sun and flowing water. They do this by hanging them from PVC trees on a monofilament line. And the PVC tree, which is confusingly named, is a PVC structure that has a central axis called the trunk and many branches coming off of that axis at different heights in the water column that hold corals that are hanging. Now, these corals, they need to grow there for months on end in order to reach the adequate size. And CRF has over 500 trees in their Tavernier nursery. That means that they have to be cleaned multiple times to counteract biofoul growth. Now, biofoul is an issue because if it overgrows the coral or even competes with it too much, the coral growth can be inhibited and it can even kill the coral. Now, in order to counteract that, CRF has been sending divers every weekend, weather permitting, 2 times a day for both days to clean those trees. And even with that, the trees are not clean enough to not send interns on the weekdays to go clean the ones that have been less adequately cleaned or have been missed. Now, when I was diving for them, I used their traditional chisel and brush method to clean the trees. What I found was that this method was actually really inefficient. The chisel, while it had enough power to break off the pieces of barnacles and sponges that were growing on the PVC, couldn't clean a large enough area of the pipe at one time in one stroke because it was flat and trying to clean something curved. So I thought, wow, it would be really great if there was a tool that could clean that whole arc of the PVC at once. And the brush, which I on land had thought would work relatively well, actually ended up being rather inefficient because it can't get rid of those tougher pieces, especially on the monofilament line like this one. So when I got back on land, I started to design something in Tinkercad that I call my biofoul tool. And this biofoul tool has a series of holes of differing diameters to clean the PVC pipes on the tree. And the top one is for the trunk, and the other ones here are for the differing sizes of PVC branches that they have, depending on the height. And very small here are the monofilament cleaning slots, which are used like this, and the monofilament slides through that slot to get cleaned. Now, this tool, which I found in its current form, the plastic version, was actually 14% more efficient. And that's with all of the errors and problems that I've encountered with it. For example, this tool, because it's made of plastic, which I 3D printed, thank you to Lance Epley from Mighty Mo Designs for helping me with much of the firmware and additional kind of information about 3D printing. Because I printed it out of PLA plastic, it actually catastrophically failed, like this one here, at the connection to the longer end of the tool from the handle. And while this is concerning, and I couldn't dive with this tool for the rest of the, I couldn't clean with this tool for the rest of the dive, the more interesting part was that it was gradually getting worn down by cleaning these tougher materials. So I have to use a new material, such as aluminum or steel even, for these new designs. Now, I had Hap Hanks from Aluminum Designs hand cut a previous version of this tool, but it's not here because I sent it to CRF and they're actually still testing it. In the future, I want to make these out of steel and CNC machine them so that they can get cut from sheets more efficiently. And according to some research I've done, each tool would only cost about $20. And I could even experiment with rough edges to make the tool more effective at cutting the most durable of the biofoul. Now, with this tool, I hope to be able to sell it around the world because many of the global organizations that do coral restoration have adopted CRF's design for trees as a standard around the globe. So hopefully with higher efficiency in cleaning, they can plant more corals on the reef and negate that die-off that has been occurring since the 1970s.
Hi, I'm Sarah Chrysler, and I'm from Fort Myers, Florida. Today I'm going to be demonstrating the ultimate tennis trader and how to use it. But before I start, I would like to give a big thank you to my parents and grandparents for helping me put together this amazing project for the science fair. So let's get into demonstrating. This is the base. It can roll anywhere on the court that you want it to roll, so you can make any shot that you want to make. Next is the center tube. It goes into the base so that you can raise and lower it for any shot that you want to make. Well, depending on your height. Next is the serving bar. You can serve from it, and you can also hit forehands and backhands off of it. Next is the ball rack. It basically just slides into one of those tubes or things. Next are the ball extenders. I'll explain them later when I get into hitting. Now let's get into hitting. Okay, so you can use either one of these depending on your height for your serve and for your forehand and backhand. So they basically just hook into those holes right there. And I'm going to use a short one because I'm taller. You have to hook it onto the holes that going out, but you have to push them like facing that way because if you don't and you turn them around, when you go to hit, they'll run into the poles. So this is what my forehand looks like, or what it should look like. So I'm going to use the same one on the backhand. It's basically the same. So this is what the backhand should look like. Okay. show you how to serve. So, for my height, I'm going to put it what I need to have it at so I can serve. Okay, that's what my serving height is. So, I'm going to put the ball on now. You can put it around this thing if it's too tall for you to get off of. Put it up. Okay. So there's grooves in it, so you can it stays in there. So you just hook it on like that. So this is what the serve should look like. That's pretty much what the ultimate tennis trainer can do.
Hello, my name is Sharma. I'm a ninth grader and my invention is called the engine panels. Last year for my Inventors Fair, as an award, I received an invitation to visit Babcock Ranch to attend the Edison Awards. While I was there, I happened to go on a tour to visit one of their solar arrays. It was very exciting, but on the tour I was observing the solar panels and I realized that the output of electricity from the solar panels really greatly diminished during cloudy weather, and even more so during rain. This prompted me to see if there was a solution to this problem. Because according to the current statistics, during cloudy weather, the efficiency of a solar panel decreases to 30 to 40%, and during rainy weather, the output drops all the way to 10 to 20%. I wanted to design a way for the solar panels to absorb the kinetic energy generated by the movement and force of raindrops. Since a solar array can be many acres in size, there's a lot of energy being exerted onto that area from raindrops falling at high speeds, which is currently all being dissipated. I needed to find a way to harness all of that kinetic energy, convert it into electricity, and embed the mechanism into the solar panels, all while not disrupting the flow of sunlight to the solar cells. I decided to utilize a concept known as piezoelectricity. This is a property of certain types of crystals with a specific atomic structure that allows them to generate a small current when applied with mechanical stress, essentially allowing the conversion of mechanical energy into electrical energy. This property would be what allowed me to create the engine panels. I also considered using other types of energy generation methods similar to piezoelectricity, like ferroelectricity, which generates electricity through the separation of positive and negative electric currents, and pyroelectricity, which generates electricity through the heating and cooling of materials. Pyroelectricity seemed to be an apt method since solar panels already produce heat as a byproduct, and solar panels can be cooled by removing the heat, which in turn improves the efficiency. However, this idea had already been thought of and created. I also had to decide what type of solar panel I was going to be using. And after some research, I came across a type of solar cell called a dye-sensitized solar cell, or a DSSC for short. This type of solar cell was unique from many others because of its price to performance ratio. In theory, this type of solar cell can achieve grid parity, which is when an alternative energy source, in this case solar, generates power at a levelized cost of electricity that is less than or equal to buying electricity from a power grid. This is a very desirable property, and this coupled with the fact that the solar cell can be easily created, made these solar cells the ideal option to use. The engine panels are a fusion of solar and piezoelectric technology, allowing for the generation of electricity through the force of rain, when there may not always be enough sunlight penetrating the atmosphere to provide a stable flow of electricity. When a raindrop makes contact with the surface of the solar panel, the piezoelectric material generates an alternating current and sends it to the bridge rectifier. The bridge rectifier then converts the current to a DC current. Electricity then flows to a capacitor and then can be made available to charge a battery. I also did some research to make sure nobody had invented something like this before. For my research on the internet, I found an article talking about the possibility of using piezoelectricity and solar panels together. However, the article specifically focused on how to utilize the piezoelectric material to clean the surface of the solar panel and did not even use rain as a source for input or power. There aren't any other similar products available in the market today, so I continued on with my invention. I did search several solar shops such as Involt Solar, Solar Illuminations, and Beacon Solar to see if a product like this existed, but I couldn't find any. I also searched on USPTO and the Google patent search, and I couldn't find a valid or active patent for a similar invention. For my first design, I tried to visualize how the design would work in my head. I needed to find a way to embed the piezoelectric material into the solar panel without disrupting the flow of sunlight to the panel. I couldn't place the piezoelectric material directly on top of the panel, otherwise it would block the sunlight. But if I placed the piezoelectric material behind the solar panel, then there would be little force exerted onto the piezoelectric material, rendering them essentially useless. I then decided to model a prototype using CAD, computer-aided design, to hold the DSSC and the piezoelectric material. I designed a module that could hold the solar cell and piezoelectric material in one piece. However, the module was very flimsy and snapped as I was trying to assemble it. So I edited my previous module to incorporate larger supports that still allowed as much sunlight to penetrate the surface as possible. I also realized that I had no way to ensure the solar panel would not slide out of the module, so for my next design, I would print covers for the sides. This would ensure that the chemicals inside the solar panels could not escape and also made it more durable. I then remembered reading about a type of transparent piezoelectric material. This type of piezoelectric material was much more sensitive and generated almost 50 times more electricity than the most commonly used piezoelectric material. This meant that I could place the piezoelectric material directly on top of the panel without disrupting the flow of electricity, all while harvesting as much electricity as possible during rainy weather. This material was known as a PMN-PT crystal. The difference in this crystal compared to others was that it was AC pulled rather than DC pulled, which allows it to achieve near perfect light transparency. Unfortunately, the transparent piezoelectric material is only for commercial use, so I couldn't create a prototype using it, but I did make a CAD model incorporating it, and it's shown here on screen. With no other design issues notable, I decided to use this third model as the final prototype for my invention. As our society starts to shift to focusing on renewable, more sustainable energy sources, solar is at the top of the list, and in its current state, it isn't possible for us to meet energy requirements with just solar energy. Through many improvements and modifications, it is my hope that one day, solar and many other renewable energies can be used to generate electricity in innovative ways. Thank you.
Hello, my name is Mehreen Chowdhury, and this is my project about a novel approach to the early detection of neurological conditions using eye movement data. Over 1 billion people, nearly 1 in 6 of the world's population, suffer from neurological disorders varying from Alzheimer's and Parkinson's disease, strokes, multiple sclerosis, epilepsy, brain injuries, and neuroinfections. Up to 450 million of these people are not officially diagnosed or treated of their conditions. The main reasons why 450 million people are not diagnosed or treated of their conditions are due to high expensive costs and lack of facilities. Performing MRI scans, CT scans, and other neurological diagnosis assessments can cost up to $500. The cost of a visit to your neurologist can range from anywhere to $50 to $500, which is too expensive for almost 70% of our population. And according to the World Health Organization, at least half of the world's population cannot even obtain essential health services. Many third world countries don't even have enough hospitals or facilities to accommodate those with neurological disease symptoms or diagnosed individuals. This is why I want to address these problems of inaccessibility and difficulty of diagnosis by establishing a website that will make it easier to detect neurological diseases and make it more efficient. My first engineering goal for my project is to create a highly accessible and easy to use application to detect eye movement data as a biomarker for neurological conditions. My second engineering goal is to have the website be completely virtual and cost-free. And my third engineering goal is to have the website be integrated with computerized cognitive tests, analytics, and computations underpinned by affordable software in order for user comfort. So I begun my procedure by first researching specific eye movement trends for different neurological conditions from research studies to be analyzed. For the second part of my project, I then used the designing for the coding using visual design code, GitHub, Netlify, and the website template was created using HTML5 editorial. For the development of my project, specific codes were integrated into the website to make the application be able to track eye movements. I integrated webgazer.js into the website. Webgazer.js is an eye tracking library that uses common webcams to infer the eye gaze locations of web visitors on a page. My fourth part of conducting my procedure was the website. I made the website to be easy to understand, and I added computerized cognitive tests in order to generate results for the user. And for the last part of my procedure, which is the data collection, I generated graphs using the data from the eye tracking results and compared my specific results to specific eye movement data for neurological diseases. This is the homepage of my website, Neurodiagnosis. You can pause to read if you want to read through the security statement, if you would like, and the introduction of the homepage. This is how my website works. The user first enters the homepage, then they take the conglomerate test. The conglomerate test can provide the fixation duration percentage in a region of interest. In this case, it's the eyes because I'm tracking eye movement, which uses the webcam to track eye movement. The areas of interest, AOIs, were defined in the conglomerate test as the dots, or the circles in the diagram. Eye movements such as saccades and fixations are then calculated with respect to the predefined AOIs, again, which are the dots/circles in the diagram. Fixations are used to calculate time spent looking at a particular location, and saccades are rapid eye movements that allow to shift between fixations and can reflect shifts in attention. The conglomerate tests saccades by using an anti-saccade test, which first tells the eyes to focus on a black dot and then introduces a new red dot. The test then advises the user to ignore the new red dot and look away from it. After the test is done, then the results are sent to a medical professional to then give a diagnosis. This is the gaze fixation versus length of animation graph for autism. The gaze fixation is the amount of time that the user, in this case is me, since I wasn't able to test anyone else for this project, spends looking at the object, and the object for my website was a circle dot. The length of animation is how long it ran for. I created the benchmarks for these graphs based on the data collection I gathered from many different studies that use very similar eye movement tests that I use for my website. The next graph that I use is the cognitive score percentage for dementia. On my previous slide, it mentions how the fixation duration and the ROI determines the cognitive score, which is shown in this graph. Again, the benchmark was determined by previous studies that I have researched. Then these are just the gaze versus animation graph for Parkinson's and Huntington's disease, and you can pause if you want to look at the numbers for that. In conclusion, my application met and exceeded my engineering goals. I addressed the problems of inaccessibility and difficulty of neurological conditions by establishing a website that used eye movement data as a biomarker of the detection of neurological conditions. In the future, I would like to be able to successfully publish the website and make it open to the public and add more software to improve the accuracy of my results. I would also like to work with doctors to improve my websites. I'm currently now working with medical professionals and to making my website available for those in rural areas with lack of facilities. These are my resources, and thank you so much for watching. Bye.
Hi, I'm Nishini, and my invention is the energy metamorphosis. Design development, idea 1, plastic pulverization. For the past few years, I have been curious to learn about the effects of pollution on the environment and climate change. In fact, I did 3 science fair projects related to this topic. One of the main issues currently facing society is the amount of plastic pollution and the room it takes up. I decided to build a plastic pulverizer that would use high wind velocity to break down plastic and create a byproduct of heat that would then be converted into electricity. Here's my home demonstration. I used hair dryers from Goodwill and a Home Depot paint bucket to mimic the high wind velocity and the chamber respectively. I placed Cheerios in the chamber to act as a model for the plastic. However, the main issue is that the velocity was not sufficient to break down the plastic Cheerios. And with the available resources, I was not equipped to increase the velocity. Furthermore, my secondary objective was to tap the heat during this process and convert it into electricity. However, no heat ended up being produced as the force was not sufficient. This made me more curious about tapping wasted heat to produce electricity, which leads me to design development, idea 2, converting waste heat into electricity. I learned about the Peltier effect in a science article and was fascinated about the possibility of simply using a heat difference to create electricity, which can then be stored and used for multiple end uses. I had noticed for a long time that the bonnet of a car gets very hot after a long car ride. However, the heat is only a byproduct and not used for the functioning of the vehicle. I noticed the same issue with air conditioning units. That's when it clicked. I could use the Peltier and Seebeck effects to convert this wasted heat into a more useful form of energy. I started out by building a cardboard prototype with 5 Peltier units on each of the 4 faces, resulting in 20 Peltier units. Next, I decided to prove the concept of how my invention would work in a vehicle. The prototype in the picture is made from aluminum. I tested the device at home using a boiling water and a pump to help with circulation. Here is a video demonstration of my invention. The boiling water symbolizes the hot coolant in the engine of the vehicle. One end of the Peltier unit was facing the hot liquid flowing through the tubing, and the other was facing the air temperature. This created the heat difference, which would in turn lead to an electricity production of 0.01 volts. I used an infrared thermometer and a multimeter to check the temperature and the amount of electricity being produced. My invention is meant to be planted between the hosing connecting the engine and the radiator. The Peltier unit uses the temperature difference to produce electricity. One side must be hot and the other cold. The larger the temperature difference, the more energy it will produce. After lots of research into a material that could withstand heat, I decided to use aluminum. My device is made of aluminum and Peltier units. A soldering iron is used to connect the wires of the Peltier unit. I use silica paste to connect the Peltier units to the aluminum because it is a good insulating material. It will cost roughly $45.76. This price can be reduced because currently Peltier units are a relatively new technology. As more research is completed and it becomes more cost efficient, it will also lower the cost of my invention. To look at my device in a more realistic environment, I took it to Lou's Total Car Care. They ignited propane to mimic the temperature of vehicles. My device had 4 Peltier units. They increased the temperature while the Peltier units were connected to a multimeter reading the voltage. At 150 degrees Fahrenheit, the Peltier units produced no voltage. The flame was then increased to a temperature of 500 degrees Fahrenheit, while the outside temperature was 180 degrees. This mimics the temperature of the bonnet in a running vehicle. It then produced 2.145 volts in DC current. As it continued to be exposed to the heat for a long time, it produced 25.61 milliamps. As per my cardboard prototype, which was shown earlier, extending the length of my invention by adding more Peltier units, for example 20, could generate enough electricity to charge the car's battery. Thermoelectric devices have already been made, however, none quite like mine. In one article I read from early 2019, the scientists mentioned that current thermoelectric devices are not practical for day-to-day use due to their cost. In 2016, a nano generator was built to create energy from the physical activity in car tires. However, this has not been widely manufactured. My invention will put less pressure on power plants and protect limited resources like fossil fuels. My invention can not only be applied in vehicles, but also to air conditioning units, thermal power plants, and steel and other heavy industries that emit heat energy as waste. Current Peltier units are only made in a square shape and have a 5% efficiency. To maximize the surface area, I was forced to make my invention as a rectangular format. In the future, I would construct my invention in a cylindrical format, the exact shape of current tubing systems. It would also be vital to examine other thermoelectric devices and potentially adapt their concepts to mine. Other cost-efficient, heat-resistant materials would also need to be examined. By doing further research, my invention will be able to generate even more electricity. This is my sales pitch. The wasted heat goes through my energy metamorphosis, which converts it into useful electricity. Here are my references. Thanks for watching.
Hello everyone, my name is Carolyn. I'm currently in 11th grade and I'm from Naples, Florida. I'm really excited to share with you my invention of a bioplastic from banana peels. I've always been really interested in the environment and I am an active member of my environmental club at my school. We always discuss plastic pollution, therefore I really wanted to take the first step towards sustainability by creating an eco-friendly bioplastic from banana peels. To clarify, a bioplastic is derived from renewable organic materials that biodegrade. As we know, artificial plastics have been greatly polluting our waterways and can take up to 1,000 years to decompose. Additionally, according to researchers, the weight of plastic in the ocean will likely exceed the weight of fish. These immense problems call for innovative solutions such as eco-friendly bioplastics. You may be wondering why I chose the banana peel, and this is a great question. Originally, I wanted to work with corn and potato skins because bioplastics are actually starch-based, so it seemed intuitive to choose these options. However, upon further research, I actually discovered the banana peel was the most suitable choice for a bioplastic. And this is because the banana would not have to be wasted to create a bioplastic, because the peels could easily be retrieved from large plantain chip companies. Whereas for a potato, it is really hard to obtain its skin without actually sacrificing its produce. And furthermore, little research has explored various types of banana peel bioplastics. Therefore, my research aims to fill this gap in the current knowledge. More information about this can be found in my logbook. Here are my materials and my procedure, and some really important materials are glycerol and sodium metabisulfite. Glycerol increases the flexibility of the bioplastics, and sodium metabisulfite is a preservative which allows the bioplastic to not decompose too quickly. Now I'll do a brief run through of my procedure, soak the banana peels in preservative, boil and dry them, add hydrochloric acid, glycerol, and sodium hydroxide, blend them in a blender, and then bake in an oven. Here are some process photos of what I did, and more about this can be seen on my display board in Michigan. So in my first trial, I looked into the Cavendish banana, which is the typical yellow banana, and I originally baked the bioplastic for 15 minutes. However, it was actually a bit undercooked. So in my next trial, I decided to bake the bioplastic for 20 minutes. And the bioplastic in this trial was actually derived from a different type of banana peel, which was a plantain hybrid. And I chose this banana peel upon further research because it actually has a higher starch content than the Cavendish banana that I used in the first trial. And then in the third trial, I again baked it for 20 minutes, the optimal bake time, and I looked into a dwarf Manzano banana. And I was really just curious to see how each of these bioplastics compared to each other, and I wanted to see how their strength compared. So that is exactly what I did. I actually measured their strength by using a fruit penetrometer. A fruit penetrometer actually functions by puncturing a hole in the bioplastic and seeing how much pressure it takes to break the material. So therefore, in other words, a higher mean kilopascal value would indicate a stronger bioplastic, meaning it took more pressure to break the material. And as you can see, the plantain hybrid had an almost twofold yield to failure compared to the dwarf and Cavendish. And then I wanted to see how it compared to what was on the market, such as an artificial plastic grocery bag. It was actually more durable than the plastic bag because it had a higher mean kilopascal value. And then here are the statistical tests that I ran, and I'll do a brief run through of them. So the first thing that I did was actually ran an ANOVA test between the banana peel bioplastics because I wanted to see where the differences among the groups derived from. And the p-value generated was less than 0.05, so therefore I concluded this was significant. So I had to follow this up with t-tests, to see how each bioplastic differed from each other. So when the plantain was compared against the other banana peels bioplastics, it was significant. However, the Cavendish, when compared to Dorf, yielded a p-value less than 0.05. Therefore, there was no statistical difference between these two types of banana peel bioplastics. And most importantly, the plantain hybrid actually did yield a statistically stronger bioplastic than that of a grocery bag, with a p-value less than 0.05, which shows that it is a plausible alternative to artificial plastics. And as I was just saying earlier, bioplastics really can replace artificial plastics in the future. I definitely think that they do have the capability to do that. And featured on the left is actually bioplastic products that are currently on the market right now from a company called Reroute. And they make their products from agave, and I'm actually fortunate enough to be doing an internship with them this summer. And as of right now, there are actually no banana peel bioplastic products on the market. So that would really be my next step in the future of what I want to do. And then lastly, as you can see, in 2030, bioplastics in general will be a $324 billion industry, which shows how profitable they can be. And I think that consumers in both companies who are eco-friendly and care about the environment will really want to purchase sustainably. And that's what I'm hoping to do with my banana peel bioplastics in the future.
Hello, my name is Yusuf. I'm in the 10th grade, and my invention is Powerwalk. Powerwalk is an innovative smart sneaker that uses thermal electricity. What are some problems that Powerwalk intends to solve? Powerwalk solves a series of 4 problems. The first is environmental pollution through the production of electricity. The second is running out of charge on electronic devices. The third is the safety of oneself. And the fourth is pedestrian accidents. How exactly does Powerwalk solve these problems? Powerwalk solves these problems through a series of 6 main components. We'll go into each one briefly and what problems they solve. First, we'll start with the TEG, which is also known as a thermoelectric generator. The thermoelectric generator produces electricity through temperature differences. This creates an environmentally friendly product as electricity will be produced through an everyday object, which is the shoe, without using fossil fuels. The thermoelectric generator is implemented with one side being kept warm, which will be facing the inner part of the shoe where your foot will go. The cooler part will face the outside of the shoe, coming into contact with the environment. It's very effective because the temperature difference will be volts will be created as long as there's a temperature difference. With the model I'm using, I found that around 1 volt can be produced with a temperature difference just by wearing the shoe. However, with the bigger thermoelectric device, more voltage will be created, which is what I would use if I was actually manufacturing the shoe. Next is the power bank. The power bank allows for the collection of volts over time and solves the problem of the relatively low producing TEG by storing the electricity continually as you wear the shoe. The power bank is implemented in the sole of each shoe through a series of wires connected to the TEG and the other components that I will later mention. It's very effective because it is able to store the volts produced by TEG, which adds up to many hundreds of volts as you wear the shoe. Within 2 hours, the power bank will be able to charge an iPhone. The next is the USB Type-A outlet. The USB Type-A outlet solves the problem by allowing electronic devices to be charged through the connection of the power bank, which is connected to the TEG. This enables the charging of an electronic device even when an outlet is not around. You can just use the outlet on your shoe. The USB-A outlet is implemented in the back of the sneaker, connected to the power bank through a series of wires. There's also a cap covering that goes over the input to protect the outlet whenever you're not charging. Fourth is the GPS device. The GPS device helps to solve the safety problem. By allowing the sneakers to be tracked, you'll be able to locate where the wearer of the sneakers is. This allows for a safety net and a peace of mind to anyone that has access to the app to track where someone is if they simply just wear the sneakers. The GPS device, like the power bank, is located in the midsole of the shoe. Next is the vibration device. The vibration device allows for a phone-free navigation experience. Essentially, you can eliminate pedestrians or drivers looking at their phones for directions when navigating a city. This helps to eliminate problems of pedestrian deaths as it reduces the risk of pedestrians looking at their phones, but rather paying attention to other vehicles when navigating around. The vibration device is located inside each shoe to the right of the toolbox area. It is connected to the GPS wirelessly and is wirelessly connected to the power bank. Here's an example to make things more clear for the vibration device. Let's say you're at spot X but want to go to spot Y. At point number 1, your right shoe's device will go off, signifying you to turn right. Point number 2, your left shoe device will go off, signifying you to turn left. And at point number 3, your right shoe device will go off, signifying you to turn right. And you'd finally get to spot Y without ever looking at your phone for directions, but rather just feeling the vibration devices on each shoe. Next is the mobile app. The mobile app functions as a manager to the sneaker. Features include the navigation input for the GPS that makes the vibration devices work, the GPS tracking and tracking of your traveling time and steps, and goal creation for fitness. What is the value of my product? The value of the product it provides real value to customers and improves the environment, giving customers a reason to buy the products, making the shoe a possible lifesaver to some. What is my evidence relating to a thermoelectric device? As you can see here, this is the volts produced relative to the temperature differences using a Peltier model thermoelectric device, which is what I used in my invention. Around 1 to 2 volts is usually the average produced when wearing the shoe. As you can see, the higher the temperature difference, the higher the volts outputted. The originality. Yes, my product is original. Although there are already some sneakers marketed as smart sneakers from various companies, none of the sneakers have the same features as mine or even the same purposes. From the smart sneakers models I found, mostly from Nike, all of them are self-lacing rechargeable shoes, which has a completely different purpose from mine. My invention solves problems unlike the other smart sneakers that are worn as a fashion statement. So no, my invention does not already exist. Using the United States Patent Depository Library, I searched up relevant keywords that can relate to my sneakers' key features, and doing this I found nothing, making me confident that I'm creating a truly unique and innovative product. What is my business plan? I would sell my product to sneakers or tech companies, also known as licensing. I could license my product to sneaker companies that are already established in the sneaker making industry. The benefit to this is that I can gain access to new markets that are otherwise inaccessible. Here's my poster that basically goes over everything that I reviewed in the slideshow. I also linked it to the Seafair's website. Thank you for listening, and I hope to talk to you guys soon.
Hi everyone,
It's an honor for us to be up here.
my name is Owen Drews,
And my name is Nicholas Harding.
and we are both in 11th grade. Ever since we were in middle school, we both had an interest in the medical and engineering sectors of design. This is what gave rise to our novel invention, Vision Bound. Vision Bound is our solution to bridge the gap between technology and preventable retinal diseases. In this case, we chose to analyze the severity of diabetic retinopathy cases and break into the market of accessible point-of-care utilities.
To provide context, diabetic retinopathy is a complication caused by an existing history of diabetes that can slowly deteriorate a person's vision and can even lead to partial blindness. Often, this diabetic complication can be treated by modern laser eye treatments. However, when left untreated, its effects seemingly take on worse results over time. These severe cases are often seen in developing nations where general access to medical testing is bleak, with most patients unsure of their severity until physical implications become apparent.
In fact, 79% of the adults with diabetes reside within low to middle income nations and serve a major risk of joining the estimated 93 million people worldwide suffering from diabetic retinopathy. Without significant medical testing, which can often prove expensive, this population is at the most risk of developing blindness and suffering the consequences of vision impairment. In this sense, the recent development of low-cost neural networks as a means of detecting early stages of diabetic retinopathy has become a much-needed solution to centuries of unknown suffering as a result of this complication. However, such solutions must be accessible as well as accurate in their results. This is the basis for our study and the reason for such urgency when it comes to developing solutions.
Our original concepts for this endeavor sought to combine the nuances of our research into one modern and expansive solution. Our products plan to incorporate our research within efficient neural networks to best suit the needs of a wide degree of low-income patients. These particular algorithms include the convolutional neural network, or CNN algorithm, and the k-nearest neighbor, or KNN algorithm, for which have proven their individual efficiency in low-cost medical testing.
We were able to verify the individual effectiveness of KNN and CNN algorithms by conducting a novel experiment. We directly compared the two algorithms across a changing training sample size. At the largest training sample size of 2,500 retinal images, CNN was over 6% higher in accuracy compared to KNN. This signifies that the CNN's accuracy could continue growing at a higher rate with additional training samples. This gave us significant evidence to suggest that CNN could effectively be used in a high sample scenario to detect DR severity, while K&N could still verify basic retinal structure for sample capture.
The results in our experiment confirmed by a two-way ANOVA study that we conducted, which generated p-values less than the significance level of 0.05. This meant the null hypothesis was rejected. From this, it can be concluded that there is a statistically significant relationship between the type of algorithm and the accuracy in identifying specific stages of diabetic retinopathy in retinal images. This means that the type of algorithm played a role in its accuracy and wasn't due to chance, proving that the results are likely valid.
Through these initial ideas, along with analysis via morphological synthesis, we had developed the concept of a point-of-care headset utility that could detect when a retina was under its scope and immediately run analysis testing as to the severity of the patient's DR.
The final configuration includes a 30D lens at a distance of 3 centimeters from the pupil that is paired with a 12 megapixel Pi high-quality camera that interfaces with the microcontroller. In addition, this design also allows for a wide range of customization via its available snap-in ports on the bottom and side. These customized utilities can interface with the product via its electronic USB-C port that also acts as a functional charger. To accompany the device, we also included a substantial battery for mobile consumption.
On the digital side of the product, we utilized a custom K&N algorithm to recognize the retina when in view and a tested CNN algorithm to discern between that sample's particular stage of DR. Once a conclusion is determined, the testing results are exported via a dynamic NFC transmitter placed under the charging port. This resulting technology allows users to hover their phones over the labeled NFC area and receive their trial results over the web. This system of exportation was primarily chosen to reduce the cost of using traditional medical records and to provide a truly accessible experience.
To perform a proper analysis, a trained professional would have to hold the device 3 centimeters away from an exposed retina and make adjustments until the external light changed from red to green. This change is a signal that represents the capture of a sufficient retinal image. Then the professional must wait a couple of seconds for the light to switch to blue. This final signal change represents the end of data processing and the availability of data.
The results from the test will be available to the patient upon hovering a mobile device over the NFC area. This pop-up would provide confidence intervals to the user that would help assess the projected severity for DR and provide simple notes as to the possible treatment for their situation. This system offers a drastic alternative to the past options that are often complex to operate and utilize outdated systems for medical record keeping.
The intended audience for VisionBound would be medical centers, global nonprofits, and medical research institutions wishing to detect diabetic retinopathy. Millions of people across the globe suffer vision complications as a result of diabetic retinopathy, attributed mostly to the lack of appropriate testing. This discrepancy can be solved through algorithmic efficiency and innovative design. Both of these aspects are a key part of our VisionBound utility.
Not only will this product modernize the market of point-of-care utilities, but it will also offer a lasting improvement to people all across the globe. Thank you to Dr. Nelson, Dr. Paul, and Mrs. Chu for their support, and thank you for your time.